Hi, everyone. So we've been talking about U-substitution and evaluating indefinite integrals, and we've talked about evaluating definite integrals using the FTC. So today we're going to be talking about kind of merging those two ideas together. So what happens when we want to evaluate an integral, but we want to evaluate it over an interval? So we're going to still be talking about U-substitution because, again, taking the antiderivative of a square root function with something underneath is probably not going to be easily done just using what we know about the power rule. So let's go to U-substitution, and we'll kind of look at two methods. So we're just going to be using substitution, then using the FTC here, and then we'll kind of talk about something else that we might be able to do that would be kind of like a shortcut. So in this particular integral, let's call u our 2x plus 1. And let's find du. And it looks like du would be 2 times dx, which is going to tell us that when we solve for dx, that's going to be du over 2, or 1/2 du. So let's do our substitution. And for right now, I'm actually going to leave off these I'm going to leave off the 4 and the 0 just for notation purposes, and we'll talk about why. So I'm going to call this the square root of u, substitute in my dx, which is going to be 1/2 du. And then I'll take my constant on the outside of the integral. So 1/2 times the integral of the square root of u du. And then I'll go ahead and turn that into a fractional exponent so that I'm able to use my power rule. So I'm going to go ahead and do 1/2 and take the antiderivative of u to the 1/2. So that is going to give us 1 over 3/2 u to the 3/2. And I'm not going to put plus c here because we are evaluating over a specific integral, so we're not dealing with an indefinite integral anymore. But I am going to clean this up a little bit. So 1/2, and that'll be times 2/3 u to the 3/2. And if I multiply this, our 2's are going to end up canceling, so that's going to give me 1/3 u to the 3/2. So then at this point, we're going to go ahead and substitute u back in. So we called u 2x plus 1. So that's going to be 1/3 times the quantity 2x plus 1 raised to the 3/2 power. And what I want to do at this point is I'm going to go ahead and I'm going to evaluate from 0 to 4. So I can go ahead and just substitute those values in. So 2 times 4 plus 1 is going to give me 9. So 1/3 times 9 raised to the 3/2 power. And then I'm going to subtract from that 1/3. When I plug in a 0 here, that's going to give me 2 times 0 plus 1. So times 1 to the 3/2 power. And then I can go ahead and evaluate this. So it's going to be 1/3 times, that's asking me to do the square root of 9, which is 3 raised to the 3rd power, so 27, minus just 1/3. So 9 over 1 minus 1 over 3. So 27/3 minus 1/3 is going to give me 26/3. So kind of the same idea as what we were doing with the FTC. The only difference is that we're kind of taking those steps with our U-substitution to get the antiderivative first. And then once we know what that antiderivative is in terms of x, then we can just go ahead and use the FTC like we would with a normal definite integral. But sometimes this actually might not be the most efficient method to evaluate a definite integral. So there is actually another way to do it. And I actually usually prefer this way because you actually can skip a couple of steps that we did up here. So method 2 says that as long as your function is continuous over the interval and f is continuous on the range of g of x, then what we can say is that the definite integral from a to b of our u-substituted function can actually be evaluated on a different interval. And that interval would be what we evaluate our u expression at. So I'll tell you what that means down here. So I started off with the same function that we actually just looked at up there. We know that the integral is going to end up being 26/3, but using the method here, basically that allows us to skip this step of plugging the u back in, and we're actually able to evaluate straight at this step. So I'm going to back up a little bit, and I'm going to go to this step where I said, okay, well, I know that when I do my U-substitution, it's going to give me a 1/2 times the integral of u to the 1/2 du. So again, same function, same interval that I was given up here. And I'm going to go ahead and again use the same power rule that I used up here. So that's going to give me 1/2 and then times 1/3/2 u to the 3/2. And again, when I cleaned that up, that was 2/3 u to the 3/2. And then we said that that would simplify to 1/3 u to the 3/2. So at this point, I'm actually not going to substitute back in that u is equal to 2x plus 1. What I'm going to do instead is I'm actually going to evaluate the function right with u. But what I need to do before I do that is I'm going to say, okay, well, we said u is equal to 2x plus 1. My original bottom limit was 0. My original top limit was 4. So instead of using the bounds 0 to 4, they're going to change, because what I'm going to do is I'm actually going to substitute them into this function to get my new bounds on the u function. So I'm going to substitute in my lower bound of 0. So this is going to give me 2 times 0 plus 1, which means that my new bound is actually going to be 1 instead of 0. And then I'm going to do the same thing with the 2x plus 1. And I'm going to evaluate at 4. So 2 times 4 plus 1 is going to give me a new upper bound of 9. So instead of plugging back in what we know to be u, which we said was again 2x plus 1, I'm going to take this function and I'm going to evaluate it straight at these new bounds starting at 1 and ending at 9, which again are the bounds in terms of u, because we're going to want to evaluate this function in terms of u instead of x. So I'm going to evaluate from 1 to 9. So when I do that, I'm going to end up with a 1/3 times 9 to the 3/2 minus 1/3 times 1 to the 3/2, which actually, if you notice, that's the same algebra that we ended up doing up here. We just ended up skipping that middle step where we had to substitute back in our u and then substitute in our bounds up here. So we said that 1/3 times 9 to the 3/2 is really 1/3 times 27, and then minus 1/3 times 1 to the 3/2 is really just minus 1/3. So that told us that was 9 minus 1/3, which again was equal to 26/3. So no matter which way you do it, you're still going to end up getting the same integral, or the same, remember that this is representing the area under the curve. This is just allowing us to streamline our process a little bit and kind of skip these steps before substituting in. So let's see. Let's look at another example. So this example is asking us to evaluate from 1 to 2 of this function. Don't be confused with this notation with the dx in the numerator. That's the same thing as writing the integral from 1 to 2 of 1 over the quantity of 3 minus 5x squared dx. So you can write the dx in the numerator, or you could also write it just kind of even with your fraction bar. So again, using u substitution, I'm just going to call u my 3 minus 5x. I'm going to call my du negative 5 dx, which is going to give me dx equal to du over negative 5, or dx would be equal to negative 1/5 du. So I'm going to go ahead and do my u substitution. And I'm going to, again, leave off the bounds of the integral for right now, because that's, again, going to change if I want to do my antiderivative in terms of the bounds that I'm going to get from u. So this is going to be 1 over u squared. And then I'm going to plug in my dx value, which is going to be negative 1/5 du. Here's my constant that I can go ahead and pull out front. And I'm going to just rewrite this 1 over u squared as u to the negative 2 power. And then I'm going to go ahead and take my antiderivative. So that's going to be 1 over negative 2 plus 1 is negative 1, u to the negative 1. Clean that up a little bit. So that's going to give me a 1/5 u to the negative 1. And if I wanted to write that as kind of something a little bit easier to probably evaluate, I can just write that as 1 over 5u. And then I have to make a decision. Do I want to go ahead and substitute back in what I know to be u, or do I want to evaluate in terms of u? Well, I'm going to evaluate in terms of u. So that means that my bounds 1 and 2 are going to be changing. And what are they going to be changing to? Well, I'm going to plug that back into this u expression up here to find out. So 3 minus 5 times 1 is going to give me a negative 2. And then 3 minus 5 times 2 is going to give me a negative 7. So my bounds of what I'm going to be evaluating at are going to be from negative 2 to negative 7. So this is going to give me, looks like negative 1 over 35 as my first term. And then I want to subtract from that negative 1/10. And that looks like that's going to be negative 1 over 35 plus 1/10. And then I'm actually just going to use my calculator here to help me out instead of making common denominators. So negative 1 over 35 plus 1 over 10. Looks like that's going to be 1 over 14. And remember that we can always go to our calculator and check our antiderivative to make sure that we are getting the correct area under the curve. It probably would be most helpful to use your original function in terms of x to do that. So what I'm going to have you guys do is I'm going to have you practice some problems using definite integrals, and then we will kind of wrap this up on Thursday. So let me know if you have any questions.